You have no idea how few audiences appreciate math jokes. We appreciate our next speaker. He is a cosmologist at the University of Helsinki, but he's also worked in places like Oxford, CERN, and Geneva. He is absolutely fabulous. Syksy Räsänen.
Thank you, Jamie. So 100 years ago, in 1915, general relativity was discovered. So this is the centenary of general relativity. And general relativity is a theory of space, time, and gravity, and it's very beautiful. So in my opinion, it's the most elegant theory of physics, and it's also one of the two pillars of our understanding of the universe, the other being quantum field theory. And I don't think it's an exaggeration to say that the unveiling of general relativity, the discovery of general relativity, is one of the greatest intellectual achievements in human history. So not just in physics, but in all of human history. And closely tied up with that is the legend of Albert Einstein. So the myth goes in short as follows. Einstein was this grizzled old man sitting alone in his patent office, thinking deep thoughts, and then in isolation he came up with the general theory of relativity. And this story is cherished by many, including by journalists, who keep on asking who is the next Einstein, which leads to headlines like this. Nowadays, sitting in the patent office has been replaced by surfing, which is surely nicer. About the reality. So first of all, Einstein didn't look like this. He looked like this. So there's this tendency that whenever we talk about famous physicists, to put up their pictures when they were these old, grizzled guys, instead of how they looked when they actually made the discovery. So Einstein was 36, younger than me, also 50 years younger than James Randi, incidentally. More importantly, Einstein did not come out of nowhere. I mean, he had a PhD in physics, and he kept in touch with the greatest physicists and mathematicians of his time, including Hermann Minkowski, who was actually his teacher. And in fact, it's quite difficult to think how Einstein could possibly have discovered general relativity, how anyone could have discovered it, without a good physics education and strong interaction with the physics community. I mean, so if you think of Pablo Picasso, I mean, do you think that he could have, without ever studying or practicing painting, have sat down and thought, okay, today I'll do something new with pictures? So, and physics is like painting or like carpentry. It's both a creative process as well as a craft. So it's something that you really learn by doing. However, in one important respect, the myth is true. Namely, Einstein unveiled general relativity with very little reference to observations, and mostly on theoretical grounds. There was one important observation which he used, which is related to the precession of perihelion of Mercury. So what this means is that so have Mercury going around the Sun on an ellipse, but the ellipse turns slowly, so it precesses. And as it's going around, then unlike in this picture, by the way, the shortest distance between Mercury and the Sun changes a bit at every rotation. And already in the 90s, and you can calculate how much it should change based on the influence of other planets. And already in the mid-19th century, it was realized that it changes too much, more than what's predicted. It's about 8% more. And general relativity explained this difference of 8%, and Einstein used this in constructing the theory. But apart from that, it was sort of theoretical consideration in mathematics, and they were really driving the theory. And that's unusual, very unusual. So usually, new theories of physics are formulated in strong interaction between theory and observation. So the way it works is that you have some theory, so you have some idea of what the world is like, then you write it down, that's your prediction, then you go out and make observations, and if they don't agree with your prediction, then you go back and make a new proposal. At least that's the idea. Now, nowadays, the theories of physics are so advanced that usually if you find that observations don't agree with your theory, then it's actually because there's some problem with the observations, there's some problem in the data analysis, or there's some noise you didn't take into account, or whatever. I mean, not that theorists are blameless, I have to say, because, and I'll let you in on a little secret, maybe it's a big secret, of theoretical physicists. Most of the theories we propose are wrong. In fact, almost all of them are wrong. It's not because of mathematical mistakes, although people do make mistakes, but simply because it turns out that they don't describe reality. So that's why it's important that you go back to observations and you say, okay, that theory is wrong, that theory is wrong, that theory, okay, these two can still be okay. And actually, even Einstein is a warning example of this. Because after the incredible success of general relativity, Einstein used the same methodology of working mostly on theoretical and mathematical grounds, actually even more so than with general relativity, to construct a theory of unified physics that would not be the general relativity but everything. And it didn't work. So something that's not often as emphasized is that Einstein spent the latter part of his career, most of his physics working life, going to blind alleys, and he didn't end up anywhere. And I think one reason for that may be that Einstein didn't have this strong interaction with the physics community anymore. So when he was formulating general relativity, by the way, he was not in a patent office. He was by that time already a professor and director of a research institute. And then when he tried to formulate these unified theories, he was at the Institute of Advanced Study in Princeton. And there's a nice sort of joke/story by Murray Gell-Mann, who was in the 1950s. He was a young physicist, and he was at the same time as Einstein at Princeton. And Gell-Mann said that if he would show his work to Einstein, Einstein didn't know what to make of it. And this was like the cutting edge of physics. And if Einstein showed his work to Gell-Mann, Gell-Mann didn't believe it at all. Which may not have been a bad attitude. Gell-Mann also says something interesting about general relativity, which is this beautiful theory and incredible achievement, which is that you have to despise it in order to get good at it. And what this means is that the way you learn physics is that when somebody tells you something, this is the way the theory is, then you say, it cannot be like that because of this reason. And you take that reason, and then you go and then you write things down, and then you find out why it actually is like that. Or maybe you find that it isn't, and you make a discovery, but usually you're just wrong. Usually you just teach yourself, okay, so I was wrong after all. And this is also the way you approach the situation if you want to find out whether general relativity actually describes the universe. So it means you assume that it's not true. You assume that general relativity is not describing the universe, and then you go out and do observations and check out, whether this is the case or not. And general relativity has now been tested with the motion of planets and probes in the solar system, and the motion of light rays in the solar system, and bending of light by the sun, bending of light by the galaxies and by clusters of galaxies, by spin-down rates of twin pulsars, by cosmic microwave anisotropies, by the motions and signals of GPS satellites, and so on. And for 100 years, general relativity has been able to explain all of these observations. Sometimes people outside of physics ask, but have physicists ever thought of the possibility that what happens if general relativity is wrong? And in fact, these ideas have been proposed since Einstein's time, and every week dozens and dozens of articles, this is only a small preview, appear discussing this possibility. And new ideas are also proposed, if not every week, then at least every month. It's just so far, there is no evidence for any of them. Now, this doesn't mean that general relativity, despite having withstood this test for 100 years, is certainly completely right. In fact, we certainly know that it's wrong on some level. At least in the level that it doesn't describe everything. Now, this is a very weak sense of being wrong. You're wrong because you don't know everything about everything. Okay. Fine. But for theories of physics, we have the domain of validity, which is some area in which the predictions of the theory should hold. So if you think of Newtonian gravity, which was there before general relativity, then its domain of validity is limited to small velocities compared to the speed of light and weak gravitational fields. So if you do a Newtonian calculation and you find out that objects are moving faster than the speed of light or close to the speed of light, you say, okay, that doesn't work anymore. You have to go back to relativity. Or if you look at the orbit of Mercury, Mercury is close to the sun, the gravitational field is strong, and you cannot trust the Newtonian gravity anymore. You have to take this 8% general relativity correction into account. And so there's the domain of validity of Newtonian gravity, which is a subset of the domain of validity of general relativity. And we don't know what are the boundaries of this domain of validity for general relativity, because we don't know what's the gravitational theory beyond it. So it's expected that general relativity will break down if gravitational fields are very strong, but we don't know how strong exactly. It's also possible that it will break down on cosmological distance scales over billions of light years, or over scales which are very, very small, which you probe in laboratory experiments. But we don't exactly know, so we're actually looking in all of these places to find out how we could be wrong. And there is some sense in which we already know where general relativity is wrong, in that there's something that it cannot describe, namely the properties of matter, which are described by quantum field theory, which is this other pillar in our understanding of the universe. And so far, we have not been able to completely combine general relativity on quantum field theory, the theory of everything, or a theory of quantum gravity. But we are also not completely in the dark. So there is a small area of overlap between these two theories if you consider the early universe, where matter was very dense, so gravitational fields were very strong, so general relativity becomes important. But also, length scales are very small, so quantum effects are important. And using this overlap of general relativity of quantum field theory in a setting called inflation, we can then calculate what sort of quantum fluctuations we should have in the early universe. We can compare to observations, and they look like this. So this is the sky in microwave frequencies, if also the world was black and white. So these, what you see on the so this is light from when the universe was 380,000 years old, on the very early universe, and these small inhomogeneities are the seeds of all later structure. So these are the seeds of galaxies, of planets, of us. Everything has been born from these random quantum fluctuations. And we can theoretically calculate, using this overlap of quantum field theory and general relativity, how the sky should look like, and it really looks like that. And we are not done yet, because these patterns may also guide us to getting to a theory of gravity beyond general relativity, or even to getting a deeper union between quantum field theory and general relativity, this theory of quantum gravity, which would be an achievement beyond that of Einstein in 1915. But that would be a whole new story. Thank you.